Hey, today we're going to look at a very important series convergence test known as the ratio test. And it's called that because it considers the ratio of a term of the series to the one before it. That's that a sub n plus 1 divided by a sub n. In particular, it considers the limit as n goes to infinity of the absolute value of that ratio. And what the ratio test says is that if that limit is less than 1, then the series converges absolutely. And we already know that a series that converges absolutely converges, and so the series converges. On the other hand, if that limit is greater than 1, including the possibility that it might be infinity, then the series diverges. It's worth noting before we go further that the ratio test tells us nothing if that limit is equal to 1, and we'll look at a couple of examples of that later on. In a minute, we'll give a quick proof of the ratio test, but first I'd like to look at a couple of examples. Let's look at the sum n equals 1 to infinity of n squared over n factorial. Or in terms of the work that we're going to do, we could just as easily be looking at the alternating series, sum n equals 1 to infinity of negative 1 to the n times n squared over n factorial, since the limit we're going to be taking is of the absolute value of the ratio of the terms. The negative 1 to the n won't affect the outcome. And just to go slow and carefully with this first example, let's work out what is the n plus 1th term, a sub n plus 1. Well, you plug in n plus 1 for n, and you get n plus 1 squared over n plus 1 factorial. And the nth term, a sub n, is of course n squared over n factorial. And so the limit we're looking for is the limit as n goes to infinity of the absolute value of the n plus 1th term divided by the nth term. This is probably the last time you'll see me write it out this way because it's so cumbersome. Dividing by the a sub nth term, dividing by n squared over n factorial, is the same thing as multiplying by n factorial over n squared. And so usually I'll skip this step and go straight to the next one, which is this right here, because dividing by n squared over n factorial is, as I said, multiplying by n factorial over n squared. And this simplifies because n plus 1 factorial is n plus 1 times n factorial. And again, in the interest of going slowly over the first example, I'll actually write that out. All I did here was rewrite n plus 1 factorial as n plus 1 times n factorial so that you could see that the n factorials are about to cancel. And after canceling them, we're left with this expression, and you can see that you can simplify it even further by canceling a factor of n plus 1 in the numerator and denominator, which gives us the limit as n goes to infinity of n plus 1 over n squared, or the absolute value of n plus 1 over n squared. Now, the absolute values are not strictly necessary here because the n's are all positive numbers. They're starting at 1 and going to infinity. And so we can just look at this as the limit as n approaches infinity of n plus 1 over n squared. And now you can either divide numerator and denominator by n squared and use the limit laws to come up with this limit, or you can use L'Hopital's rule since it's of the form infinity over infinity, and one way or another, however you do it, this limit is equal to 0. And more importantly than what it's precisely equal to, this limit is less than 1. And so the ratio test tells us that this series converges. So we can conclude that our original series, sum n equals 1 to infinity of n squared over n factorial, converges by the ratio test, or if we were looking at the alternating series, we can say that it converges absolutely by the ratio test. Let's look at one more example before we get around to explaining why the ratio test works. The sum n equals 1 to infinity of n to the n over n factorial. We have to consider the limit as n approaches infinity of the absolute value of the n plus 1th term divided by the nth term, and the n plus 1th term is n plus 1 to the n plus 1 divided by n plus 1 factorial. And then dividing by the nth term, dividing by n to the n over n factorial, is the same thing as multiplying by n factorial over n to the n. And here I've done the same simplification that I did in the last problem. N factorial divided by n plus 1 factorial is just 1 over n plus 1. In other words, n plus 1 factorial is n plus 1 times n factorial, and the n factorials cancel. So that's all that we've done to get to this step. And then also, as we did before, we can cancel one factor of the n plus 1s. So that's why the n plus 1 has disappeared from the denominator. And in the numerator, we no longer have n plus 1 to the n plus 1. We just have n plus 1 to the n. We can drop the absolute values since all the terms here are positive. And then n plus 1 to the n over n to the n is the same thing as n plus 1 over n all to the n. And although it might not be strictly necessary, I'll rewrite this as the limit as n goes to infinity of 1 plus 1 over n all to the n, in the hopes that perhaps you will recognize this limit. You have certainly seen it before. In particular, in first semester calculus, this was sort of the pinnacle of the L'Hopital's rule problems. You had to use some cleverness, let y equal this limit, take natural logs of both sides. There was a bunch of tricks that were required. And in the end, we found that this limit is equal to e. And this is sometimes taken as the definition of the number e. The limit as n goes to infinity of 1 plus 1 over n to the n. We tend to not take that as the definition in Calc 1, but instead prove that this is true, as I said, using L'Hopital's rule. One way or another, this limit is equal to e, and e is greater than 1, and that's the point. Because that tells us that this series, the sum n equals 1 to infinity of n to the n over n factorial, diverges by the ratio test. Okay, let's look at a proof. We'll look at the two parts of the ratio test individually, and so we'll start with the first one that says that if the limit as n goes to infinity of the absolute value of the ratio of the terms is less than 1, then the series converges absolutely. And so we'll start by assuming that this is indeed the case. This is this first line right here. Suppose that that limit is equal to some number L less than 1. And if L is less than 1, then I can pick some value R, with r between L and 1. And the idea that this limit here is equal to L is the same thing as saying that these terms, absolute value of a sub n plus 1 over a sub n, get arbitrarily close to L if you go far out enough in the sequence. In particular, if you go far out enough past some number n, then you certainly can assume that past that number n, this ratio is less than this value r that we picked, which is bigger than L. And then if you take this expression that we have right here on this line and multiply both sides of the inequality by the absolute value of a sub n, then you get exactly this expression right here. And that says whenever n is greater than or equal to this value capital N, then we always know that the absolute value of the a sub n plus 1th term is less than the absolute value of the a sub nth term times r. And in particular, that's this next line right here. If we let our n be capital N and then capital N plus 1 and then capital N plus 2, etc., then we get, well, for capital N, that this statement right here, that the absolute value of a sub capital N plus 1 is less than the absolute value of a sub capital N times r. Things get more interesting when you consider little n equal to capital N plus 1. That gives us this line right here, that the absolute value of a sub capital N plus 2 is less than the absolute value of a sub capital N plus 1 times r. But we already know something about the absolute value of a sub capital N plus 1. That's this expression right here. It's less than this expression, absolute value of a sub capital N times r, and we've already got the one of the times r's there, and that's where we get this absolute value of a sub capital N times r squared. And doing it one more time and moving on to the capital N plus 2 term gives us this line right here, which tells us ultimately that the absolute value of a sub capital N plus 3 less than absolute value of a sub capital N times r cubed. And if you proceed in that manner and look at the general case, you get that the absolute value of a sub capital N plus k for any positive natural number k is always less than absolute value of a sub n times r to the k. And the beauty of that is that this series, sum k equals 1 to infinity of absolute value of a sub n times r to the k, is a convergent geometric series. How do we know? Well, we know that r is some positive number less than 1. And so it's a convergent geometric series. Meanwhile, the terms a sub capital N plus k are less than the terms of the convergent geometric series. And so that tells us that this series converges by the comparison test. And then the final punchline is that if this series converges, so does this one, which is the one that we were interested in from the start, because they differ by finitely many terms. In particular, they differ by the first capital N terms, however many they are. So if this one converges, so does that one. And that's the proof of the first part of the ratio test, the part that tells you when some series converges absolutely. Moving on to the second part of the ratio test, that part tells us that if the limit of the absolute value of the n plus 1th term over the nth term is greater than 1, including the possibility that it might be infinite, then the series that we're interested in diverges. And so to prove that, we'll start by assuming that that happens, assuming that the limit that we're looking at is greater than 1. And the idea that that limit is greater than 1 means that we can find some natural number capital N such that if we go out past the capital Nth term in the sequence, then we always get that this is true, that the absolute value of a sub n plus 1 over a sub n is greater than 1. That's whenever n is greater than or equal to some number far enough out in the sequence. And then multiplying both sides of this by the absolute value of a sub n gives this expression right here, that the absolute value of a sub n plus 1 is always greater than the absolute value of a sub n once you go far enough out in the sequence of terms in the series. And the beauty of that is that it means that there is absolutely no chance that the terms could possibly be converging to 0. They're always greater than some positive number, and so they can't be converging to 0. And if the terms don't go to 0, then we know that the series diverges. And so that's the proof of the second part of the ratio test, and now we've done the whole thing. I'll give you one to try for practice in just a moment, but first I want to show you what happens if we apply the ratio test to these two series. These two series we've seen plenty of, and we already know the answer. The first one is the harmonic series. We know that it diverges. The second one is a p-series. We know that it converges. And for the first one, if we take the limit as n goes to infinity of the n plus 1th term, which is 1 over n plus 1, divided by the nth term, which is divided by 1 over n, so times n over 1, we get 1. I've dropped the absolute values because all of the terms are positive here, and so we don't need them. But the point is that we know that this series diverges. The ratio test doesn't tell us that. The ratio test tells us absolutely nothing in this case. When the limit of the ratio of the terms is equal to 1, no conclusion can be drawn. And the same thing happens for this second series. If we look at the limit as n goes to infinity of the n plus 1th term over the nth term, we again get 1. We know that this series converges, but the ratio test doesn't tell us that. So the moral of the story, ratio test, very powerful test, very useful in all sorts of situations, and yet there are other situations where it's completely useless, and you need some other way to determine whether a series that you're looking at converges. Okay, you try this one. See if you can use the ratio test to determine whether the series sum n equals 1 to infinity of n squared over 2 to the n converges or diverges. Pause the video, take your time. When you're ready, start it back up, and we'll see how it goes. We have to look at the limit as n goes to infinity of the n plus 1th term, which is n plus 1 squared over 2 to the n plus 1, divided by the nth term, n squared over 2 to the n, and dividing by n squared over 2 to the n is the same as multiplying by 2 to the n over n squared. This kind of situation is going to occur a lot, and you're going to need to know from the properties of exponents that 2 to the n plus 1 is just 2 to the n times 2, or 2 to the n times 2 to the first, and the exponents add in that case. And rewriting it that way makes it clear how you can simplify this expression. In particular, 2 to the n over 2 to the n plus 1 is 2 to the n over 2 to the n times 2, and the 2 to the n's cancel, and you get what's left over here. And after you expand the numerator, this is the limit as n goes to infinity of n squared plus 2n plus 1 over 2n squared. I don't care how you take this limit so long as you come up with the right answer. You can use algebra and the limit laws. You can use L'Hopital's rule. One way or another, this limit is equal to 1/2. And the point is 1/2 is less than 1. And so that tells us that the series we're looking at, the sum n equals 1 to infinity of n squared over 2 to the n, converges by the ratio test. Okay, that was the ratio test. It's extremely, supremely important. And so there's, of course, a homework on it. Give it a good shot. Talk to you about it in class. Looking forward to seeing you then. Bye.